Hello learners, welcome back to the channel Pen and Paper Chemistry. Are we ready to continue with the topic of amines? Yes, today we shall be talking about the chemical properties of amines. Don't forget your pen and notebook. I'm sure you must be having a separate notebook by now. So let's get started. Now as we start with the chemical properties of amines, there are some important points that you need to remember. First of all, that these are derivatives of ammonia, NH3. Now here the important element that we are talking about is nitrogen, electronic configuration 1s2, 2s2, 2p3. This 2s2 pair of electrons, which actually does take part in hybridization but not in bonding, is what we call as the lone pair of electron. Now because of this lone pair of electron, it is capable of showing certain unique behaviors. First of all, because it has a lone pair of electron, it is able to call a proton towards itself. So our NH2, it has a lone pair of electrons. I have a proton over here which is hungry for electrons. This NH2 can offer its electron pair to the H positive, becoming a protonated molecule itself. Now because it is an electron donor, it donates electrons, hence it's a Lewis base. Remember, according to the Lewis concept, Lewis acids are electron acceptors. So A for acid, A for acceptor, whereas Lewis bases are electron donors. Similarly, if we compare it we compare it to the Bronsted concept. Now here, because it is accepting a proton, according to the Bronsted concept, so Bronsted acids are proton donors, whereas Bronsted bases are proton acceptors. So we can define proton acceptors, yes. So we can define a substance as acidic or basic in different formats or on the basis of different theories. So Lewis concept is more to do with electrons, whereas Bronsted concept is more to do with protons. So on the basis of both the concepts, it's a proton acceptor, a Bronsted base, it's an electron donor, so a Lewis base. So all in all, it is basic in nature, just like our ammonia, right? Now, because it has electron pair which is available for bond formation, it loves something which is positively charged. That means it is nucleus loving. Hence, we will notice some very interesting reactions of amines. Also remember over here, when you have alkyl groups, so if I am comparing the basic character, so this is ammonia, has no alkyl groups. On the other hand, in the case of NH2, so when you are talking about a primary amine, there is an alkyl group. Now what is the nature of alkyl groups? Alkyl groups are electron donating. They donate electrons towards nitrogen which is already electron rich. So when it donates electrons or when it is directing electrons towards the NH2 group, what will happen to the density of electron cloud? Yes, density of electron cloud increases. Now because this density of electron cloud increases around the nitrogen, will it become more basic or less basic? Yes, it is capable of offering electrons easily. In other words, it will become more basic. What if I add one more alkyl group to it? That means I am talking about a secondary amine. Yes, of course, the basic character increases. What about if I add one more alkyl group? So again, the basic character is going to further increase because our alkyl groups are electron releasing. So if I talk about basic character in gaseous state, we notice that our amines follow the order tertiary greater than secondary, greater than primary, greater than ammonia. Now I have used a very important word over here, and I have said that this is the order that they follow in the gaseous state. That means there is no solvent which is involved. But why should I worry about the solvent being involved or not? Yes, there is a logic to it. So what we have over here is more the number of alkyl groups, more the electron donors, and more the basic character. Have you written this down? Now we mentioned in the previous slide that this order of basic strength is very much applicable when you are talking about the gaseous state of the amines. That means there is no solvent involved over here. No solvent means no solvation. Remember what solvation does? Yes, it may help to release energy and make it more stable. So no solvation means no release of energy, and that means less stability as well. So no release of hydration energy, and there will be less stability of the ion. Now how does this change, or how does it affect the basic nature of amines? Let us try and understand. And what are the factors other than solvation which affect the basic character? So when I talk about basic character in aqueous solution, first of all, what I have done is I have highlighted the order that we observe of basic strength. You see, it's neither reverse nor the same, it's something different. Here we notice that our secondary amines are actually most basic when compared to tertiary and primary. And anyway, amines are more basic than ammonia. So ammonia definitely remains at the bottom of the ladder, but 1 degree is more basic than ammonia but becomes less basic than 3 degree, that is tertiary amines. How and what affects this? There are various factors. The first one that we've already spoken about is the plus I effect, that is the electron releasing effect of the alkyl group. More the number of alkyl groups, more is the plus I effect, and more is the basic strength. So this favors what? Yes, of course, it favors the 3 degree, that is the tertiary amines. That means this should be the winner. Second is we spoke about solvation, because we are talking about an aqueous solution. Now remember, in our previous video we said that primary amines, because of more number of hydrogen attached to them, are able to undergo hydration easily. So have I drawn the correct structure over here? Look at it and tell me. Yes, because we are talking about hydrogen bonding in the cation which is so formed after gaining a proton. So now there are 3 atoms which are available to be solvated or to undergo hydrogen bonding with the water molecule and in turn get solvated. In this case of secondary, it is only going to be 2. In the case of tertiary, there is possibility. Is there any possibility? Yes, only 1. Let's try and understand what I have done. Ammonia in water forms an equilibrium with ammonium hydroxide. Look at what has happened. H positive, OH negative. This forms a bond, NH4 positive, OH negative. Now here again H, OH. It forms a bond. So it's forming an ammonium cation. Similarly here primary ammonium cation, secondary ammonium cation, tertiary ammonium cation, and each one of this is forming a hydrogen bond with the water molecule depending upon how many hydrogen atoms are attached to the nitrogen. This is what we call as our solvated ammonium cation. That means the ammonium cation formed from the respective molecule. Here this solvated ammonium cation has been formed from a primary amine. Similarly, we will form one from a secondary and a tertiary. More the number of hydrogen atoms available, more the solvation, more stability. More solvation, more stability, because here there will be attraction between the two, and because of that attraction there will be release of energy, more release of energy, and more release of energy means more stability. Now here obviously our primary is a clear winner when we talk about solvation, but there is another factor which comes into play, and that is the steric factor. What is steric factor? Here is our nitrogen. When somebody tries to approach the nitrogen for its electron pair, you see this R, that we are simply writing this R as an alkyl group. This is actually H, H and H. Or if it is an ethyl group, then what is going to happen? It is C, and then there is H, H and an H over here. Look at the way it is expanding its wings, and what does it do? Now if somebody tries to approach the nitrogen, do you think it will allow easily? No. And that is what we call as steric hindrance. More bulky the groups, bulkier the groups, more the steric hindrance. So I am now going to, so in other words, when we talk about steric hindrance, then in that case obviously our 1 degree is the clear winner, because it has only one alkyl group and the rest two are hydrogen. In the case of secondary, there is one hydrogen but there are two bulky alkyl groups. In the case of tertiary, as we have seen, that there are 3 alkyl groups. So according to, in this very reasoning, with this steric hindrance, or obviously our 1 degree is a clear winner over 2 degrees and 3 degrees. So what are the factors that we have studied so far? First we said plus I effect, and in the plus I effect it is the tertiary which is a winner. Then we spoke about hydrogen bonding, and when we spoke about hydrogen bonding, it is the primary which is the winner. And then we spoke about steric factors, and here again our primary is the winner. Now while the 1 degree and 3 degree are fighting with each other, where they lie in this order, it is 2 degree which has advantages of both the steric, plus I and hydrogen bonding, and that makes it come to the top of the race. So while the 2 cats are fighting, the monkey takes away the slice of cake. So we have 2 degree, greater than 3 degree, greater than 1 degree, and greater than ammonia. So the basic character of amines is definitely higher than that of ammonia itself. So in case you want to take down the notes, I'm going to keep it on the screen. So you can either write it down, you can always pause the video, and then we go on to in the aqueous solution, Go ahead, you can write it down. Remember that when we are talking about the extent of hydrogen bonding, we are talking about the substituted ammonium cation and not just the original amine, because we are talking about an aqueous medium. This part of the equations is just to clear the concept for you. Have you written? So now remember the three factors that we spoke about: steric, solvation, and inductive. Now these are the three factors which control the basic strength of amines, and on this basis we had said 2 degree, 3 degree, 1 degree and ammonia. But remember the factors. So that is why we've given examples over here. When I'm talking about substituted methylamines, meaning to say I start with ammonia, that is my NH3. Now I replace the hydrogen atom by one methyl group. I'll have CH3NH2. Now replace 2 of the hydrogen atoms by methyl group. I'll have CH3 whole twice NH. I will replace all 3 hydrogen by methyl groups. I'll have trimethylamine. Now here, so if we are comparing, now here this methyl group is actually relatively small. So with the result, what will happen is the steric factor will not have as much role to play as if this alkyl group was bulky. With the result, the order of basic strength remains as secondary, primary, tertiary and amine. Clear? So here what is playing the role is the plus I effect of the alkyl group and solvation. So here solvation is more, solvation is more, whereas here solvation is less. So the order of basic strength, when I'm talking about, see over here, I'm talking about methylamines. That means the hydrogen is replaced by methyl group, replaced by CH3 group. On the other hand, if I am talking about ethylamines, that means we start with ammonia, we replace the hydrogen by an ethyl group. Now look at the size of that group. Now I replace 2 of the hydrogens by a methyl group. I replace all 3 hydrogen by 3 methyl groups. 3 methyl groups, big, steric hindrance is more. So basic character increases, but because of the steric factor, it decreases. Solvation, none. Look at C2H5NH2. Now here there is steric hindrance, but to much lower extent as compared to tertiary. Electron donating effect, that is the plus I effect, and yes, the solvation effect comes into play. Here secondary stands at an advantage, followed by tertiary, primary and then ammonia. Look at the flip that has happened from primary and tertiary and primary. Let us now compare the basic character of aromatic amines with aliphatic amines. Would you like to give it a try yourself? Look at the structure, just draw the structure of aniline and see what are the various canonical structures which are possible. Is there any resonance possible in the case of amines, and what effect does this resonance have on the behavior or on the capacity of aniline to donate electrons from its nitrogen atom? Is it possible or not? Go ahead, draw the canonical structures. You will see the answer yourself. Now remember, see what I am drawing. Aniline, the nitrogen shares its lone pair of electrons with the carbon. With the result, this acquires a double bond character and my nitrogen acquires a positive charge. The electrons which were here in the pi bond move towards the carbon and the carbon acquires a negative charge. Overall, my molecule is still neutral. Now, resonance. Remember, we did resonance, so with the result, electron movement. So this now becomes a double bond and here is a negative charge. Next canonical structure, again, draw the electron and here we have. Remember, there's a pair of electrons over here. Don't forget that. Okay. Now, when it has moved, with the result, we'll have a positive, we'll have a double bond and a double bond here. Next step, electron moves to form bond with the carbon. With the result, the electrons go back to the nitrogen and we in all have how many canonical structures for aniline? 1, 2, 3, 4 and 5. The first and the last one appear quite similar, but they are not. Look at the position of the double bond in both the molecules. You will see that they are two canonical structures. Now, next step, we said that when it takes up a proton, it becomes protonated ammonium molecule, RNH3 positive. So just like ammonia becomes ammonium, same way RNH2 will gain a proton and form RNH3 positive. For the 4 it will be RNH3 and overall carrying a positive charge. So this now becomes a protonated amine, an amine to which a proton has become attached. Now what about the stability? You see, I have put an alkyl group over here, but when I am talking about aromatic compounds, aromatic means instead of this alkyl I will have a benzene ring, an aryl group. So let me put it like this, ARNH3 positive. Now, is our protonated aryl amine as stable as our aniline? And what is the reason for the stability of the aniline? Yes, the canonical structure. So let us look at this. Our aniline gets protonated and forms anilinium ion. Just like we have ammonium ion or ammonium cation, now from aniline we have anilinium ion. Here our nitrogen has acquired a positive charge. So the only possibility of a canonical structure is where these double bonds move within the ring. And we have these two structures interconverting between each other. Look at the number of canonical structures that we've drawn for aniline. 1, 2, 3, 4, 5. Look at the number of canonical structures that are possible for anilinium ion. Yes, of course, our aniline has much higher number of canonical structures, due to which it will be more stable as compared to aniline. What is the gist? What is the point of saying all this? Yes, that means aniline will not like to move from a stable to a less stable arrangement. It will try to stay this way. So that is why they do not. So their basic character or basic strength for aromatic amines is actually lower than that of aliphatic amines. And as you can see, the points that I have written over here, you can copy them down as well. I will keep them on the screen for you to copy. Remember the methylamines and the ethylamines. Remember to draw the structure so that it's easier for you to understand. Now this is the comparison for aromatic and aliphatic amines. Don't miss out on the canonical structures. Try making them yourself so that it is easier to recall at the time of exams, because that's where the biggest struggle lies. The examiner cannot go into your head to know what you know. You have to put it down on paper, and you will do it best only if you write what you see here on the screen. Remember to move the electrons around properly. Look at the two canonical structures for anilinium ion. Now another interesting fact is, now in this aniline RNH2, how will the presence of other groups affect the behavior of aniline or affect the basic strength? If I have groups which are electron releasing, what we call as the EDG. EDG means they are giving electrons towards the benzene ring. If they are giving electrons, that means they won't want more electrons from the nitrogen. In other words, that resonance will not be possible so easily. In fact, they are giving, boss, take electrons from us and share it with something which is in need of electrons. So what will happen to the basic strength of the amine? Yes, it is actually going to increase. So electron donating groups increase basic strength. What are those groups? These are groups which will have electron pair on them which they can share with the benzene ring. On the other hand, if I have a group which is electron withdrawing, so electron withdrawing means here is my benzene ring and I have some group like NO2, which instead of giving electrons pulls away electrons from it. Now when it pulls away, now benzene is short of electrons, and you know that our benzene likes to play the dodgeball game. So what it does is it tells NH2, see boss, my electrons are being pulled towards the NO2, why don't you share more of some of your electrons with me? Now the electrons, the lone pair of electrons on NH2 are being engaged by the benzene ring. If they are being engaged by the benzene ring, do you think that they are available now to form a bond with H positive? Do you think it will try to form into anilinium cation or nitroanilinium cation so easily? No. So that means the basic character actually goes down. So that is what we have written, electron withdrawing groups. For example, NO2, SO3, COH and halogen, they actually decrease the basic strength of the aromatic amine or the form of it. Have you noted this down? I'm going to allow you to share copy the notes in your notebook. I will also be posting these on the Google site, Pen and Paper Chemistry. So don't forget, the name itself says what you have to do. You have to keep a pen and paper or notebook in your hands so that you can practice these, or you can take down notes for offline reference. We shall continue talking about the basic character of amines, wherein we shall be dealing with the quantitative aspect of their basic character, and we will see the validation of our arguments when we see the pKb values. Now what is this pKb? Don't worry, we will discuss it in the next video. So please Remember to keep your pen and notebook with you when you watch the next video in the series. See you soon. Take care. Keep smiling.